Is there anything? Yes?
How do you do cube root on calculator?
All right, so there's two things. If you push your math button, you see that sucker? The math is on the left side.
Yeah.
Here, let me put it up here. That's an easy question. There are a couple of problems in this to solve it graphically, so you have to know how to tell the cube root. One way, just directly, a cube root is also a what? 1/3 power. So if you have to graph cube root of x, you just put in x to the parentheses 1 divided by 3. If you put this in your calculator, x to the 1 divided by 3, it's going to graph x over 3. Do you guys see that? Because the calculator understands order operations. So it's going to do power, and then it's going to do, oh shit, so I better do this. So it does x to the 1/3 power, right? There's another way to do it. What's the matter? Oh, I said that really sucks a lot. Dang. There's always somebody that's messing with cables and stuff, and then they don't put it back to normal. So if you hit the math button, do you see this fourth one down? That's the cube root. The next one down, I call this one the fruit button, right? I am fruit. If I want to take the 7th root of 812, right? I can do the 7th root. That's why I call it the fruit button. 7th root of 812. There you go. So if you multiply that number by itself 7 times, you get 812. You guys follow? So now if you have to graph something, you have to graph the 5th root of something. You can do 5 math. The 5th one down, the 5th root of x. And then it will graph it. There you go. So that we've actually seen something like that before. We did the cube root. And it's got that extra piece back here that a square root wouldn't have because, there you go, you can actually see it now. It has that extra piece over here because it's allowed to be negative. It can have negative inputs and it can have negative outputs because it's an odd root. Is that cool? Yes. So like I said, you could also do 812 to the 1/7 power. It's going to be the same answer because they both represent the 7th root. So there's 2 different ways to do that. That's another reason why I wish we would just have the one way of doing it, just rational exponents. And then you just always would do the same thing. It's crazy. Cool. So anything else from homework stuff? All right. So just to remind you guys what we did last time, we ended up with a problem like this here. Well, let's do 2 here. So if I had something like square root of 2x minus 1 minus 3 equals, x minus 5. Yeah, I like it. That'll work. Yes, good. So the first thing you got to do is isolate the radical, right? So add 3. Rad 2x minus 1 equals x minus 2. So for some reason, this is so weird. This happens so much. The x just disappears from the first step to the second. Like maybe he won't notice. Because there's an x there. It's got to still be there. So if you isolate your radical elements, so then you can do what? Square both sides. So you can kill that prison. Right, that square root symbol is like a prison that the stuff is stuck in. Oh yeah, prison break. So 2x minus 1 equals, please dear God, it's not x squared plus 4. Right, you got to write that thing twice, FOIL it out. X squared minus 2 minus 2 minus 4x plus 4. And then, so is that decent? If you have a radical in your equation with a variable inside of it, you know you're going to have to square at some point to kill that radical so your x is able to be solved for. What do I do now?
Set it equal to 0, combine like first.
Yeah, I got to get it equal to 0, and then I can factor. All right. And what's telling me to do that is this stupid term there. If that wasn't there, I would just add 4x, add 1, divide by whatever's in front of the x. Right? But that's there. Shit. So I better do it this way instead. 0 equals x squared minus 6x plus 5. How do you factor this? Yeah. 5 times 1 is 5. If they're both negative, they add to be negative 6. So we get x equals 5 and 1. And then you got to check. Right? So always go to the very original before you did anything, because you could have immediately made a mistake. So you want to check those in the original. 5 times 2 is 10, minus 1 is 9. Square root of 9 is 3, minus 3 is 0. And 5 minus 5 is 0. So 5 works. Notice how I can tell that 1 is not going to work because there's a negative here. But 2 times 1 is 2, minus 1 is 1. Square root of 1 is 1, minus 3 is negative 2. And 1 minus 5 is negative 4. Not equal to each other. Not an answer. That's the only answer. I like it. Good. I like it. We did talk about why it's not math's fault that it gave you more answers. It's the only way it can tell us, oh, there's a problem here. Okay, maybe. And then we did a problem where there were 2 radicals in it. And then you just have to square twice eventually. You get one of them by himself. FOIL, it would square both sides, which normally means a FOIL is going to happen. Get the radical by itself again. And then FOIL again. I square again. All right, so we did one like that yesterday. Okay, cool. Okay. There are a couple more things in section 10.6. One of them I'm going to kind of hold on to until we talk a little bit about chapter 11, to be honest. I'll come back to it before you out here today. The other one is just... What was the other piece, Jeff? Oh, yeah. What's the Pythagorean theorem? Yeah. So this is good old Greek dude, Pythagoras. He had a bunch of followers who did all his work for him, and then he took all the credit, but oh well. So if I call this side A, side B, and we have to call that one side C, what kind of triangle does this have to be? You guys remember? It only works for right triangles. Shoop. Have to have a 90-degree angle. The formula, there's still a formula if it's not a right triangle, but it just has an extra term on it that makes it really kind of gross. But it's just kind of an adjustment for it not being a right triangle. If you go into 176, or take pre-calculus, you'll learn that bigger thing. It's called the law of cosines. Oh, shit. So, yeah, the Pythagorean theorem says a squared plus b squared equals c squared. And really, there's about 53 proofs that I know of for this. One of our presidents actually liked to try to create new proofs. It was one of the Roosevelts. I can't remember which one. This is it's not a proof, but it's a beautiful visual. If you imagine a square coming off of here, so it's A by A. And you imagine another square coming off of here, so it's B by B. And you imagine a square coming off of here, so it's C by C. What's the area of that square? It's A by A. A squared. The area of this square would be B squared. And the area of this square would be C squared. So I'm saying the area of this square plus the area of that square equals the area of that square. And there's actually this cool video online. I was going to look it up, but I'll let you guys. Where they have water. They have this thing that they can spin. And they have this on the bottom first, so they fill it up with water. And then when they spin it, these two fill up perfectly. So it shows you the area that's in here is equal to the area that's in those two. It's kind of nice. It's kind of nifty. Okay, that to me is nice. It's not really a proof, but it's a nice visual to remember. It's squares in the equation because it's squares that you're related. Okay, cool. I like it. So that's going to pop up in this section because since they're squares, if you have to solve for one of these, you're going to have to take a square root. So that's why they threw it in this section. Okay. So now we're going to get into this complex number section, right? And the word complex is a lot better than imaginary. A complex number. Let me see. I think we're going to show you the video first, and then we'll talk more specifics. All right. So I told you I was going to show you a little video. I'm not going to tape it because you can find it on the YouTubes, on the internets.